Imagine you're asked to invent something new. It could be whatever you made from anything you choose in any shape or size. That kind of creative freedom sounds so liberating, doesn't it? Or does it? If you're like most people, you'd probably be paralyzed by this task. Without more guidance, where would you ever begin? As it turns out, boundless freedom isn't always helpful. In reality, any project is restricted by many factors, such as cost, what materials you have at your disposal, and the unbreakable laws of physics. These factors are called creative constraints, and they are the requirements and limitations we have to address in order to accomplish a goal. Creative constraints apply across almost all professions to architects, artists, writers, engineers, and scientists. In many fields, constraints play a special role as drivers of discovery and invention. During the scientific process, in particular, constraints are an essential part of an experimental design. For example, a scientist studying a new virus would consider, how can I use the tools and techniques at hand to create an experiment that tells me how this virus infects the body's cells? And what are the limitations of my knowledge that prevent me from understanding this new viral pathway? In engineering, constraints have us apply our scientific discoveries to invent something new and useful. Take, for example, the landers Viking 1 and 2, which relied on thrusters to arrive safely on the surface of Mars. The problem? Those thrusters left foreign chemicals on the ground, contaminating soil samples, and so a new constraint was introduced. How can we land a probe on Mars without introducing chemicals from Earth? The next Pathfinder mission used an airbag system to allow the rover to bounce and roll to a halt without burning contaminating fuel. Years later, we wanted to send a much larger rover called the Curiosity. However, it was too large for the airbag design, so another constraint was defined. How can we land a large rover while still keeping rocket fuel away from the Martian soil? And in response, engineers had a wild idea. They designed a sky crane. Similar to the claw machines at toy stores, it would lower the rover from high above the surface, and with each invention, the engineers demonstrated an essential habit of scientific thinking, that solutions must recognize the limitations of current technology in order to advance it. Sometimes this process is iterative, as in, how can I make a better parachute to land my rover? And sometimes it's innovative, like how to reach our goal when the best possible parachute isn't going to work. And in both cases, the constraints guide decision making to ensure we reach the objective. Here's another Mars problem that is yet to be solved. Say we want to send astronauts who will need water. They'd rely on a filtration system that keeps the water very clean and enables 100% recovery. Those are some pretty tough constraints, and we may not have the technology for it now. But in the process of trying to meet these objectives, we may discover other applicants of inventions that result. Building an innovative water filtration system could provide a solution for farmers working in drought-stricken regions, or a way to clean municipal water in polluted cities. In fact, many scientific advances have occurred when huge failures in one field address the constraints of another. When scientist Alexander Fleming mistakenly contaminated a petri dish in the lab, it led to the discovery of the first antibiotic, penicillin. The same is true of synthetic dye, plastic, gunpowder. All were created mistakenly, but went on to address the constraints of other problems. Understanding constraints guides scientific progress, and what's true in science is true in many other fields. Constraints aren't the boundaries of creativity, but the foundation of it.